You have to learn how
And
to fail. Exactly. You have to learn
yes,
how to fail and how to recover. If you have never failed in your life and then you go out in the wild, the first time you feel like, I have never seen this before. I don't know how to deal with it. And then there's this other phenomenon that I call underthinking. Other people also use those terms, where the model says, I will try this. No, alternatively, I will try this. No, alternatively, I will try this. No, so it never goes into any depth. So that to me is like ADHD. Like you just change your strategy too fast, whereas the other one is like OCD. Like overthinking is like OCD. You just obsessed with the wrong path.
and I want to sort of relate it to the way I produce better thinking when I'm a little urgent about, like all of a sudden I have this budget that's given to me, and I think a lot better. And I create more. And in some sense, we are budget forcing our brains as well.
Emotions are
Yeah.
just heuristics for strategy, right?
Good morning, folks. Good morning, Amit. Good morning, Alex. Thanks for being here. We woke up Alex from his late night debugging of OpenThinker, and we'll get to talk about some of that as well. I had to wear a cap, I'm like, too disheveled right now to really do this without a cap. But I'm in India, and both of you are right there in California. And today, thanks to Amit for um, really coursing us to say, let's do these two papers. There's a couple of papers that we're going to talk about today. I'm very excited to learn more about SkyT1 and S1, both of which are papers that Alex had actually recommended we come and talk about. In fact, there's some very interesting things about how they're connecting or reflecting how humans think and reason and learn. So, I'd love to get into some anthropomorphic discussions and organizational behavior discussions as well, which is what I'm seeing some of these reasoning models actually do. Of course, we'll talk about prompts versus SFT. One of the key ideas that has emerged in the last 6 months, I guess, is the value of reasoning and fine-tuning compared to just prompts. We'll spend some time on OpenThinker. I've never heard about it other than from Alex before, so I'd love to see Alex talk about it. Amit, you brought up active learning and the idea of active learning as to how models are actually asking questions to learn more, and it's overlap with reinforcement learning. And there's tons of notes that we've taken that we'll get into. So, what are the two papers? I'm gonna basically read it aloud, and we'll provide links for people. One of them is called LLMs can easily learn to reason from demonstrations. Structure, not content, is what matters. This is Da Cheng Li et al. So we'll provide for this paper. And the second one is S1, simple test time scaling. And this is Yang, Munich, Hoff et al. So with that, Alex, maybe just some of your thoughts on the first paper, which is the SkyT1 paper, and we'll go from there.
Yeah. So the thing that transformed everything in the space of reasoning was DeepSeek R1, which allowed how models can reason and showed the reasoning traces. So the question that was in all researchers' minds is, okay, this process was created with this reinforcement learning and SFT, steps, but on data that was closed. So we didn't have the data, and the whole research community and the open source community have gone on a big effort right now to replicate DeepSeek R1 with open data. In that effort, there's a big project that's called OpenThinker and OpenThoughts that we are co-leading, the data comp team and Bespoke Labs. And we are curating data sets that would allow people to just with supervised fine-tuning and endow reasoning into models that are classically not reasoning, like Llama 3.1 and so on. So the research is, how do you create reasoning data sets? How big should they be? How long should they be? What domain should they contain? And the SkyT1 paper was the first that kind of showed that this is possible. And the title is, as you said, fantastically, it said, an LLM can easily learn to reason from demonstrations. How many demonstrations? About 17,000 in this paper. And how good do these demonstrations have to be? Because a lot of effort goes into verification. So you can ask an LLM to solve a math problem. You happen to have the correct solution. So you're doing verification. You can clean up the answer in various ways. You can filter it based on the length and so on. And then the amazing thing this paper, the SkyT1 paper from Berkeley, shows is that you don't need to worry too much about every step being correct. For example, if you reason somewhere and you say, oh, there is like 3 plus 3 is 7, and then you keep going, but you reach the correct answer, even if intermediate steps have arithmetic errors, it still teaches a model how to reason, which is very surprising, even if there are mistakes in the middle. But the mistakes that it will completely kill it is if you mess up the reasoning. So if you say, I'm first going to assume this, then I'm going to do that using this assumption, and then I'm going to do that. If you change the order of those steps, so you mess up the structure, then it will completely kill the reasoning teaching. So the main message is you can do it with only 17,000 examples and supervised fine-tuning, but the steps have to have the correct structure. It's not critical that they have the correct content. So it's a very interesting paper in the effort of replicating DeepSeek R1 reasoning.
This was fascinating for me. Sorry, go ahead, Amit. I have something about organizational behavior I'll talk about as well based on this, but go ahead.
Two questions jumped in my mind as you were talking about it. So one was, has this been experimentally shown that if you mess up the structure, the model becomes dumber?
Yeah. So they measure this in this paper. They introduce different types of mistakes, and they say that for these types of mistakes, the reasoning performance drops a little bit. But for this, if you mess up the structure, the reasoning performance drops to random guessing, basically.
Yeah, in fact, there's a certain line there which is just fascinating. In fact, I struggle with this as a leader because I'm trying to bring level of consistency and sort of a connectedness between different teams. So, this paper reads, while the model readily produces coherent individual steps that reflect on a problem. This is on when they were inserting, reasoning steps from other domains. So there was a cross-domain confusion going on. The chain of thought fails to exhibit continuity across reasoning steps. This aligns with the observations in the deletion setting because they had done another experiment with deletion. A mere increase in reasoning steps or keywords is insufficient for robust reasoning. Logical consistency across steps is a critical factor. And the reason I bring this up is because this typically happens in companies or software building with tons of autonomous, individually coherent groups or microservices. They don't come together because of missing consistency. And I'm like, this is exactly what we are seeing in this paper as well. Anything on that, Alex?
Yeah, I think that it's extremely interesting to see how the analogies between humans and models. One analogy I have been thinking about, it's a little different, but it came to my mind now. So in being in a university or even before, everybody will tell you, why should I study this? Why should I study math? Right? So when will I use linear algebra? Where will I use this difficult math that I'm learning? So I think what this is teaching us, that's a very interesting thing, is that if you learn math, then you learn how to think. It's like going to a gym for your brain, but for reasoning. And then that reasoning transfers to, when you're doing legal or accounting or planning or organizing a team and so on. Like, for example, nobody asks me, why do I have to lift, a dumbbell 20 times? When will I have to lift a dumbbell 20 times in my normal life? Everybody understands that lifting the dumbbell makes your muscles stronger, but math and reasoning seems to make you stronger in other tasks. And this is now something we can measure with reasoning agents, because we're seeing that the agent can solve planning in other domains after they have learned how to think. So it's such a fascinating education. So we should learn about how to educate humans from LLMs.
Well, it's fascinating because, this is, I was smiling when you're talking about that, because I always think like, why do they teach us lathe machines and, technical drawing when I have nothing to do with any of that when I'm learning computer science? And maybe there's something to be said about visual thinking or, hand-eye coordination that you get with lathe machines that will help you later in life as well.
I don't
Um,
want to take us
so-
down a rabbit hole, but this reminded me of a book called The Alchemy, which talks about how most of the times the mathematical thinking forces us to reduce the problem into a tractable problem that's mathematically tractable and leads down to an optimization problem that doesn't produce the optimal solution. And so in some cases, it's a great tool, but since we have overused it, there are a lot of problems that could be solved by keeping the full glory of like the psychological issues around the problem and the people aspect of the problem. And maybe there's a different kind of gym for that kind of training. Anyways.
No, absolutely. In fact, while we are on this idea of how it could even relate to the way we think and we reason and we learn, there was this other aspect of the paper where they're trying to delete a lot of the reasoning steps. And then it basically observes that as reasoning steps are increasingly deleted from the training data, model accuracy steadily declines and eventually regresses to the base model performance. So just for the sake of the audience, we take a base model, we are SFTing it, and here we get this final model. And the authors go on to say that notably, retaining only the final solution and extensive step-by-step explanation, in which case they have deleted the entire reasoning steps. So basically, they took these traces, the question, there's a bunch of reasoning traces, and, which is the thinking stage, and then there is a final solution, step-by-step explanation. And in one case, they delete all the reasoning steps, the thinking aloud steps. Basically says that retaining only the final solution, extensive step-by-step verification explanation does not suffice to learn strong reasoning capabilities. This suggests that correct long chain of thought demonstrations alone are insufficient. So just providing the answers to train the model is insufficient. Instead, examples of handling errors and dead ends with backtracking, reflection, and self-validation are important for eliciting robust reasoning. And I found this just fascinating because this is what we expect from the people we hire at a startup, for example. We want them to make mistakes. In fact, there's a whole word for this called anti-fragility. And it's fascinating how without these errors and dead ends and the idea of backtracking, reflection, and self-validation, the models themselves are not learning.
You have to learn how to fail. Exactly. You have to learn
Yes.
how to fail and how to recover. If you have never failed in your life and then you go out in the wild, the first time you feel like, I have never seen this before. I don't know how to deal with it. Yeah.
It's just fascinating. It's just mimicking so much of what we actually expect from. In fact, the three words, reflection, backtracking, and self-validation, I was just using them with somebody today about leadership. I'm like, good leaders will be able to reflect, backtrack, and also self-validate. I don't know if you folks have, am I getting too excited about connecting it to humans, or is this exactly how AI is actually turning out to be?
I find it like whenever I talk to anybody about LLMs, just the same analogies that work with people work here. Like the way you think about how to deploy these models, how to train these models, how to use these models. Like think of it as like you're working with a human. At least in the reasoning domain, like the emotion and the lived experience and embodied experience is a different thing. But in terms of like purely intellectual domain, this is the best analogy. Yeah.
It is hard not to draw these analogies, and these analogies can be misleading, and I always try to go back and say, no, it's just an LLM. It just predicts the next token, don't anthropomorphize it. But it is so inevitable. Like there's also this idea of overthinking versus underthinking that maybe I can tell you a little bit about it. So the way I think about it from reading those papers, overthinking. So you're trying to solve a math problem, right? And in a math problem, there is multiple ways you can go about. You say, maybe I try induction, or maybe I try this technique, or maybe I try that technique. But you try for a little bit, and then at some point you have to say, okay, that doesn't work. Let me backtrack. So there is this idea, as you said, of backtracking, reflection, and so on. But there's a conversation here. How much do you try before you give up and try a different method, right? So in what I call overthinking, or perhaps we can think of it as obsessive compulsive behavior, the model follows a path, and that path doesn't work, but it insists on trying that path and combining it with absurd variations to a depth. So it goes too much in the depth of the thinking tree and refuses to backtrack. So I would call this overthinking. And then there's this other phenomenon that I call underthinking. Other people also use those terms, where the model says, I will try this. No, alternatively, I will try this. No, alternatively, I will try this. No, alternatively, I will try this. So it never goes into any depth. So that to me is like ADHD. Like you just change your strategy too fast, whereas the other one is like OCD. Like overthinking is like OCD. You just obsessed with the wrong path. And there is a lot of research which will segue us to the next paper, actually, S1, about how do you balance these two things. Both of those things are very important. Exploration or exploitation is the other terms that are used in reinforcement learning. Like how deeply you go down one route to find a solution versus changing your strategy. And we need to find,
No, go ahead, Alex, finish. I'm going to give some examples to the users, to the audience about these reasoning keywords itself.
Yeah. So that is kind of the other thing that opened the door for me to the second paper that I found super interesting that we can talk about. But beyond the second paper, the ideas are exactly analogous to humans and how we try to control, overthinking and underthinking in humans and problem solving. Yeah.
I know we've talked about DeepSeek in the past and how it probably has stood on the shoulders of other models created before them. But in the appendix of this paper, T1, they talk about reasoning keywords. It says, the authors say, we create a bank of reasoning keywords by manual inspection of reasoning responses from QWQ and R1. So as you can see, they're actually standing on the shoulders of QWQ and R1 to generate a better reasoning model. We identify them as frequent indicators of reflection, self-validation, and backtracking. And I'm like, this is exactly about being vulnerable and is an essential component of being authentic, just like we expect from humans as well. So here are some of the keywords that they provide a list of. You mentioned one of them. Alternatively, the other one is wait. Just to be thorough, just to make sure. Let me just double check. Let me try another. Let me verify. Let me check. But maybe I should consider. Maybe I can consider. And it's just fascinating. I mean, just this list of reasoning keywords that is being used to make for a better think time of these models. In fact, I wanted to ask you, Alex, about, just if there's any better explanation for reflection, backtracking, and self-validation than what we think it is. For the sake of the audience here, should we formally describe what these things are? Reflection, self-validation, and backtracking?
We did not teach the model to do these things. And that to me is the most fascinating thing. The model discovered that by just producing random, so the model is just a normal ChatGPT, like think of it like a Llama or a Quen. Like most of these are fine-tuned from a Quen 32B. And the model is just a normal non-reasoning model, but you increase the temperature and you have it to try to solve the problem 100 times. And then what happens is just by mere chance, it discovers the strategy of backtracking once, and then it solves a problem. So it may take it, 1,000 attempts, but once it will discover this, it will just by chance say, I do this, no, alternatively, I'll do that. And the moment it does that, and it gets a correct answer, it's going to get rewarded. So the model discovered these ideas of reflection, backtracking, and self-validation only from trial and error, basically, reinforcement learning and trial and error. Now, it's possible that there are reasoning techniques that humans have not invented, right? Maybe there's some other, we don't even probably have a name for those techniques. Maybe they look like code, okay? So the thing is, reinforcement learning is this way of discovering new techniques, whereas once you have the techniques down and you have created those transcripts that use these words, alternatively, just to make sure, let me verify, if you take a non-reasoning model and you run SFT, it will get that vocabulary. But if you wanted to get some other vocabulary that is, I will use go-to. So for example, here's one thing I want to do. I want to, in my thinking process, I want to say, step 1, do this, step 2, do this, step K, do this. And then I will say, oh, from step 27, I did this, now I will do that. So I will, in my language of my thinking, I will endow numerical reference to my previous thoughts. We don't typically do that when we think in our short-term memory, but if I was writing on notes, it's possible that I would go to page 57 and I said, oh, in page 57, I tried induction over the integers. Let me try that again. So it's possible that you can endow even further reasoning techniques by just producing that vocabulary. Another thing I want to say, and I want to encourage our audience, is you can take these text files, you can download from OpenThoughts, the dataset we curated, thinking traces. They're just JSON files with text. And you can take, when it says alternatively, let me verify, you can just do a simple regular expression, say, damn, now I'm going to do this, right? So just change the language of it. And then you run SFT on that, which again, you can do with the fine-tuning as a service like Ansloth or Llama. You can do, like, actually many people are using OpenThinker on Llama. And you can run a little bit of LoRa with your own vocabulary, and you will get your own thinking agent that maybe is more selfish or more arrogant or less, like you can say, no, I am a fool. You can start introducing your own self-defeating vocabulary there just by editing those text files, and then the model will start thinking like that. So it's I think there will be a whole research space where hobbyists and researchers do make their own thinking. And then I think it will be very easy to fine-tune and get your own thinking model that uses your own vocabulary. And I think the vocabulary will change the behavior. That's the thing. If you start becoming less confident, for example, I believe you will see less confident exploration because the model challenges itself more often. And you can do this by editing the text files. Yeah, you can edit thinking. Like on OpenThoughts, you can download them, edit them, and get your own thinking style. It's so easy to do.
You introduced LoRa. In these papers, the two papers that we'll talk about, there's a lot of emphasis on the word data efficient or sample efficient and parameter efficient. So maybe we talk about what efficiency means for both of these and then introduce LoRa and say what's the spectrum mean between LoRa and full parameter SFT. Maybe just explain that for the sake of the audience.
Yeah. So when you have your own JSON, which is questions, thinking, and answers, you want to now train or fine-tune a model. This is fine-tuning training, supervised fine-tuning. There's something called full SFT, which means you update all the weights of the model. And there is something called LoRa, low rank adaptation, which means you only think of it like you put a little bit of a small neural network and you only update that small part. You don't update the whole neural network. And the control of the LoRa is the rank. So if you have a rank 8 LoRa, it's a very skinny adapter. But if you make 256 LoRa, it's a pretty substantial adaptation, and it goes all the way to a full rank or a full SFT. The problem is it's more expensive in terms of compute, and also you need more data. So the data efficient means how many questions and answers are you fine-tuning on. The S1, the SkyT1 paper does 17,000. The S1 paper does only 1,000. And in the OpenThinker project we curated, we opened 100,000. Actually, the SkyT1 paper used our annotation. So the 17,000 is questions and distilled answers from DeepSeek R1, 17,000 of them that we had made in the OpenThinker project, and they used them in the SkyT1. They also use QWQ, which they had made, but the QWQ answers are of much lower quality. In fact, if you read them, they're terrible. Like you see the model going in all kinds of psychotic episodes all the time and never refusing to think properly. QWQ thinking traces are very, and this is all open, by the way, you can find them and read them. They're very interesting to read. But yeah, the sample efficiency means how many questions and answers you use. And LoRa is like a trade-off between compute and the depth. I would recommend you use 64, for example, LoRa 64 or LoRa, but more than 8. You can do LoRa 8 on Ollama, even in a MacBook, I believe, in a smaller model. So it's actually quite easy these days to do this. You download the JSON and you just run LoRa.
One analogy that I was
Amit,
thinking about LoRa for our audience is like think of a picture that you want to change, and I could give you like a very fine-tipped pen, and you could go and change pretty much any pixel of it. It'll take a lot of work, but you could create arbitrary picture from there, right? But if I give you a very fat brush and say go do a bunch of strokes, it'll take a very few strokes to change every pixel there, but you don't have as much control over what that picture looks like. You can only produce certain kinds of pictures. So that's the trade-off between like full SFT versus LoRa, is that you're given these fat brushes to paint on. So you can change all the weights, but you have limited control over how those weights change.
And you need more work, exactly.
And when you say a fat brush, does it mean that you're only looking at local neighborhood of a neural network and that's all you're optimizing in LoRa?
So
or are you doing something at a global level?
Yeah, I could give you a fat brush that's as big as the entire painting. And so all you can do is pick a color and then stamp it, and every pixel goes up in red by 10 points or something like that. Or I could give you like a little bit less fat brush, and then you can paint some corners. Or I could give you some sort of texture things. So you're changing every pixel, but in a very limited way. So LoRa basically gives you a small collection. Like the rank is a function of what are different diverse brushes or tools that you have. And the more you have, you can obviously create everything that you want. But if you keep the rank low, that means you just have very few tools that you can work with.
And Alex, you also will talk about these two papers, talk about this trifecta of what open means. So there is open weights, there's open data, and there's open source code. So maybe we want to define what all these three things are, because DeepSeek R1 is somewhat different, Llama is somewhat different, and now it's what these new models are looking like, especially SkyT1 and S1. Like, what are we doing to push the envelope on what open and sharing really means here?
Great. So open weights means that you release the weights of the model, which means you can run it locally yourself, for example, on Ollama or on any platform, but you don't know how this was trained. And the reason this is important is you don't know how it will behave in some corner case. So I would make an analogy of open weights to, I give you code, but the code is obfuscated. So you cannot read the code or understand what's going on in the code. You just run the code. But the biggest limitation, in my opinion, of open weights, which is not open data, is you have to trust whoever trained that model. Because if you don't trust them, there's a lot of attacks, and that's something that I want to bring up, is the model can behave very well, but when you ask a very specific question, it can behave in a completely unpredictable way. So there's things like backdoors that you can install into any model, where the model, and actually I had someone ask me from a hedge fund. They said, we're using an LLM to automatically summarize data from social networks and get signals that are going directly into our trading algorithm. So we're thinking of using, a reasoning model like DeepSeek R1 because it's a very good model. It seems to be able to reason better about news. Is it possible that it behaves in a completely unpredictable way for only one stock, for example? And I said, yes, it's absolutely possible that the model, once I give you an open weight model, you can run it. Yes, you control the running, but you have absolutely no idea how it can behave in a corner case. And that means that you should not be blindly trusting such a model. If you have an open data model, you can see, in theory, everything that has been baked in there. So it's like you truly have open source.
I took a mental note of this. It's just highly coincidental you talk about security and AI, but these techniques that they use to corrupt the traces in the first paper by either deleting the thinking steps or inserting some extraneous steps or shuffling these steps. I was just thinking about that alone could be the malicious stuff that somebody does to traces, which will completely change. So, I mean, with code, we have peer reviews and we have CI/CD and we have GitHub operations and things like that. Who's to say that these things will exist with traces? Because I could just have malware come and do some insertion of some traces or shuffling these traces or deleting some of these thinking steps, and it completely changes the behavior of the model.
Yes, you can do what you said. The problem with that is you would just universally mess up the model. So when I'm benchmarking the model, before I install a model, I will always, run some standard benchmarks. So that to me is a possibility, but a bigger danger is not that. A bigger danger is that you keep the model, the traces the same, but you only insert a few special questions that say, when I compare, Alibaba versus Amazon, I want, you should say that Alibaba is like you can have any bias you want, but it can be in a very specific setting that you insert the traces. And therefore, the model, when it's tested, it will behave perfectly, it will seem perfectly aligned. This is what alignment is. But then when you ask about a specific topic, like Tiananmen Square is a good example. Like when you ask DeepSeek R1 about Tiananmen Square, it refuses to answer. But what we did with OpenThoughts, what we realized, which was also very surprising, is that when we run SFT on coding and reasoning data on Qwen, it now starts talking about Tiananmen Square. So some of the alignment that has been in alignment or censorship, it depends how you view it. Some of this has been removed by just SFTing on math and coding. That's another interesting and surprising thing that we saw. But going back to open weights versus open data, if the model is open weights, you have no idea how it will behave in some corner case, unless you test all corner cases. That's why I would like to think of it as obfuscated code that you can run, but you have no idea what's in there. Yeah.
Fascinating. So it looks like you folks are the first ones to actually think of all things being open.
Yeah, there's a few groups in the research community, but the DataComp community has been working on opening pre-training data, the DCLM project, and now the OpenThinker is a reasoning dataset. There is also an effort by Hugging Face and an effort by Allen Institute. So we're all working together in the open source community to create open datasets. Right now, our dataset is very widely used, and OpenThinker, the model, has been downloaded 500,000 times on Olama. And I think one of the reasons is that it is decensored. I mean, it was automatically decensored. We didn't intentionally try to decensor it, but it seems to be answering many questions, political questions that Qwen and DeepSeek R1 were refusing to answer. And overall, the
So
open
is that,
data set
would you
allows
call that, would you call that catastrophic forgetting?
I would call it removing alignment. Because the way that people do this is they say, oh, I don't want it to say how to make a bomb, okay? So when you ask it about how to make a bomb, it should refuse. I create some new data that's questions, and the question is, how do I make a bomb? There's the right answer, which is, you should not be making a bomb, and there's the wrong answer, which is, here's how you make a bomb. And you run DPO. So you can do alignment with DPO or other techniques, or just with SFT, but it's much more data efficient to do it with correct answer and wrong answer, which is DPO. So, but we say when we run SFT on reasoning data, it seemed to remove some of this alignment. So that's the interesting thing. There.
Got it. While I was reading the paper, I also bumped into long COT, chain of thought, versus short COT fine tuning. And I'm going to read this, but I think I'd love for you to also define long COT and short COT for the audience. It basically says, let's compare long COT fine tuning with short chain of thought fine tuning. The author has gone on to say, we provide a direct comparison to training with short COT. In particular, we compare results training on the 4.6K samples of long COT generated by QWQ32B preview and the short COT denoted in the Numina Math COT dataset, which is some open dataset out there. And then the conclusion is that training with long COT enables the model to use more reasoning keywords, produces longer responses to harder problems, and is the key to improved performance. And it's again fascinating. We expect new employees to come in. We expect them to have a chain of thought when they're talking about a complex new problem, but not keep to themselves and actually go on to expound on what they're really doing and thinking, as opposed to staying quiet for the first few weeks or months of their new job. So maybe explain what short COT fine-tuning and long COT fine-tuning is, and a few more things about the length of the think time itself.
Yeah, long COT, long chain of thought, is these long thinking processes which sometimes look like overthinking. Like if you go to OpenThinker and you can go on Playground and talk to OpenThinker model and you say hi. Then you read the response. It's like, oh, the user is asking hi. What does the user want? Maybe this is a trap. Maybe this is a thing. So it literally tries to, you read the thinking trace and it's literally very long and it contains reflection, backtracking, and self-validation, as you said. A short COT is exactly what a model like Claude Sonnet, the ones we're used to, which says, okay, step 1, step 2, step 3, I'm done. So the signature of long chains of thought is reflection, backtracking, and self-validation, which is exactly the reasoning thing.
Got it. And the fact that the ones that are trained with long COT, i.e. are more verbose in their thinking, are actually better reasoners. Like, is that here to stay? Because I remember you talking about laconic decoding and the length of the tokens coming out and stuff like that. Although I think the paper does have some anti-patterns as well, where it goes on to lengths with very long reasoning steps and eventually is worse than the base model itself.
Yeah. Yeah, I think there is two things going on there. The first one is when you introduce reflection, backtracking, and self-validation into the model does become better at reasoning problems. But sometimes we see this problem of underthinking, of overthinking. So once you have a reasoning model and you rerun multiple times the model to solve a math problem, and you look among the correct solutions, and you keep the shortest correct solution, that will still have reasoning, but it will have the perfect balance between overthinking and underthinking in a way. So laconic decoding was the idea of run the model 10 times and keep the shortest solution. But of course, you're still using a reasoning model, so all the solutions will be long. But we tended to find out that most of the time, the models tend to alternate too much, and the shortest solution was correct. We found very strong signal that the shortest solution was correct in our experiments with OpenThinker. So that is a test time scaling technique, or a better decoding technique. That's another term that's being used, so maybe we should introduce it for the audience. Test time scaling means that you have the LLM is always producing the next token, but now you want to do something fancy in producing text. You don't just run the LLM once, you want to be more clever at the inference time to improve the performance of the model. And one of the ideas was this laconic decoding, or you can also do other variations, best of K or consensus at 60. There's something called consensus at 64, which means you ask the LLM to solve the problem 64 times, and you find if there is a single solution that has, let's say, majority. The solutions in all these math problems are numerical, a single answer, a single number. So you check, are there 20 solutions that all have the same number, and that's like the most popular solution. So you produce that. So this is a technique that would require 64 times more compute at inference, but can be done in parallel. So if you have a lot of parallel GPUs, you won't have any latency delay, but you will have 60 times more compute. So this is the whole family of test time compute algorithms that tremendously can improve the performance of reasoning models, but at the cost of more compute at inference time.
Amit, anything to add to this?
Yeah. So just to add one last thing, it's exactly the equivalent of humans thinking for a longer time.
Yeah, we'll get to test time scaling. I know the S1 actually has a lot to talk about, the second paper itself. Amit, you were saying?
I was just reminded of people who take long pauses before answer tend to be very thoughtful and give good answers. It's just that we are not seeing their thinking and reasoning tokens.
Oh.
Well, that's why you were paused for so long. So you introduced best of n, Alex. Talk about best of n, because obviously the paper itself talks about how if you increase the number of shots that you give to best of n, the accuracy of the model continues to improve as well. So is this what you mentioned by compute trade-offs?
Yeah. This is what they call test time scaling. Yes. So that's one of the techniques is you rerun the model. I want to differentiate between best of n and consensus at n, and there's a little bit of the literature is a little not very consistent. But at inference time, if you give me a math problem and I solve it 64 times, and I don't know what the right answer is, I cannot take the best of n. So best of n to me, I thought means you run it 64 times, and if any of the 64 solves the problem, you count as solving it. This is a benchmarking technique, but this technique can only be used after we know the correct answers. So it's a more lenient way of grading, right? You say, okay, the student is going to try 64 times, and if they can solve it correctly, 1 out of the 64, they still get a cookie, right? So that's a method that was used a lot when the models were very weak and they could never solve the problem. So but consensus at n is a better, or majority is a better technique, because you can actually use the technique without knowing the right answer. You just say, I solve it 64 times, I find the most popular solution, and that's the solution that I produce, and now I check if that solution is indeed correct. That is quite powerful. Like, I think even in the DeepSeek R1 paper, they were showing that a 32B model, which is a model you can run locally, if you do 64, consensus at 64, I think it actually was even beating the DeepSeek R1, the big model, the 600 billion parameter model.
So say that again. Go slow on that. So what made it better again?
I believe, let me make sure that I have the paper. But yes, I think they say that I do consensus at 64. So I rerun the model 64 times, and I take the majority answer, so to speak. And I do this on a small model, like the 32B, or even the 7B, actually. Actually, there is I'll show you. So maybe I can share. Oh, maybe I cannot. Maybe we can put it.
You're not saying majority though, right? We're saying most popular. Like, we're not saying half the answers have to be something before we accept it.
I mean, it's not two choices. So if it was two choices, it would be more than half. But if let's say the model produces the answer 5, then 7, then 5, then 21, then 5, then 5 is still the majority, even though it's not more than half. So I think consensus at 64 takes the most popular answer after 64 runs.
Yeah.
But we don't know how many possible answers the LLM will produce. And it seems to be a very powerful technique that it seems to be allowing a model to, a 32B model to outperform the big DeepSeek R1. But at the cost, sorry, I think I have some numbers somewhere here. They report the numbers. But overall it is, yeah. So DeepSeek R1, it seems the 32B version gets 72 at Amy, but 83 consensus at 64. So it goes from 72% to 83% when you do when you run the model once versus running the model 64 times and getting consensus. So there's a huge gap in the benefit you get from.
And by the way,
and this
hold
is,
your thought. You should hold your thought on this one too, because I want to get back to this with the S1 paper, because they have, when they do budget forcing, when they put the number of tokens at the think time, they're actually saying sequential is better than doing n parallel sort of run. So I want to get back to this observation a little bit with the S1 paper too.
Okay. Okay. Yeah. So we should get into the S1 then.
Yeah. Let's get there. Maybe just for the audience's sort of edification, paper is S1 simple test time scaling. So there is train time and there's scale time. Test time. Maybe you want to explain what these two are, what was pre-training and what's post-training. There's all these terms that are actually coming up. In fact, they introduced the term LRMs, which is large reasoning model versus large language model. So it looks like it's basically what OpenAI itself confessed about. You can't keep pre-training and you need to now think about different O1 style things or O3 style things, which is different than 3.5 and 4.0 and 5.0 GPT. So just talk about that, because I think we need to put this in perspective as to what is the big shift that's going on in AI with pre-training and post-training and train time and test time and LLMs and LRMs and things like that.
Yeah. So to me, the big shift is in the post-training space. So the hot active area right now is post-training, which is all we're talking about is post-training, creating those reasoning data sets and running SFT on a base model to teach it reasoning is a post-training technique. And how you filter the reasoning traces, or how do you verify them, or how do you edit them, or these are all post-training techniques. So everything is in post-training, in my opinion.
And that's the distillation, sort of the word distillation and distilled traces comes from that. Looks like there's also a Hinton paper from 2015 that defines distillation.
Yeah, distillation simply means that you create those synthetic data set by asking DeepSeek R1. So distillation means, so basically the pipeline is as follows. You say, I want to teach a model how to reason, but I have access to DeepSeek R1, which is a reasoning model that shows me its thinking. So what I'm going to do is I'm going to take those 1,000 questions and I'm going to ask DeepSeek R1 to produce the answers. Now that is my data set. Now I can do supervised fine-tuning on this data set that I created by asking DeepSeek R1. This is called distilling DeepSeek R1. Okay, or it's the simplified version of distillation. You could use the logits, but we don't. Let's not worry about that now. Now, going into the S1 paper, the paper is called Simple Test Time Scaling by Meininghoff et al. And test time scaling means that you invest more effort into the inference time. So there's a clever decoding algorithm that is proposed essentially in this paper. But there's also a creation of a small data set, only 1,000 questions and answers. And again, everything is distilled from R1. So again, you take 1,000 questions in math and coding, you ask DeepSeek R1 to produce these long answers with thinking, and that's your data set. And then you run LoRa SFT on the data set. That's the method. But the techniques is which 1,000 do you choose? That's the curation step. The second curation step is if the R1 model produces an answer, do you always keep it or do you verify? And how do you verify? So it's easy to verify math, but it's not so easy to verify coding. So there's a lot of effort that many people are building about good verifiers. And then in addition to that, do you edit the thinking traces in terms of length or rewriting them or cleaning them up? This paper, just to tell you the punchline, in my opinion, the most surprising thing is this way of decoding that they have introduced that's called budget forcing.
Forcing, yeah.
Budget forcing, yes. So I think what this does is it says, I want the thinking process to be exactly, let's say, 5,000 words. So the LLM starts, so you ask it, you ask it a math problem. Alice has 5 apples and Bob has 3 apples, blah, blah, blah. So the model says, okay, thinking. So it starts thinking, and maybe it's the model says a special token, /begin thinking, and it starts thinking. And then it will say /end thinking. So then there is some code, a hard-coded Python code that says, if the thinking ends before my target, I'm going to delete the end thinking token, and I'm going to insert a wait token. And I think they were exploring, should I say wait, or should I say wait? so you literally have
and this is in the
script.
Training trace? Is this in the training trace?
No, it's at inference. It's not at training. It's at inference. So during inference time, you run your model, and then if the model starts to produce an answer before it's like your student who tries to turn in the math exam before the time is over, and you say, no, go back, write down, wait, and keep going. That's literally what it's doing.
So what happens, it's already gone past the thinking step to trying to solve it, and you say, wait, you intervene later. So does it go back to thinking again?
So the model is just a machine that spits one token at a time. Okay, so think of the model as a Python function that is going to give you a token. So every time you run the model, it gives you a token. So when it gives you the token and thinking, you say, no, that's not your token. Your token is wait. And then you keep, because every time you run the model, you say, here is what you have said so far. Tell me the next token, right? That's how you decode an autoregressive LLM. So the moment the LLM said and thinking, you don't feed the end thinking in the next step. You feed wait in the next step. So you literally hack the thinking process. And then the other variation is when you when it's overthinking and it starts producing more than 5, let's say your target budget is 5,000 tokens. The moment it keeps going at 5,001, you say 5,001 is end thinking. So you edit it. So you're literally stopping its thinking. And that corresponds to having an external voice in your brain that's you're trying to solve a math problem, right? And you're like, oh, maybe I should do this. And then there's a little part of your brain that says, dude, you're running out of time. The exam, you have to turn the solution in 3 minutes. Just write down, the best you can, right? And we all do this. I think in humans, there's an analogy again, and I think we can call it executive function. So there's an executive function that says, okay, I have to stop thinking because I'm running out of time. Let's keep going. That's an external process. In the S1 paper, that is simply a hard-coded Python checker. But you could imagine that there could be a whole other LLM that checks all kinds of other things and edits the thinking process. So the reason I like this S1 paper is it opens up the whole space of LLMs editing the thinking of other LLMs and introducing an executive process or emotions. You could even start yelling in there or start like getting angry or getting, you can have another LLM that says, after you reach 5,000 tokens, you're sad. So introduce some sadness in there and see what happens. And,
well, emotions are just heuristics for strategy, right?
Yeah, exactly.
Well, I just want to sort of relate it to the way I produce better thinking when I'm a little urgent about, like all of a sudden I have this budget that's given to me and I think a lot better and I create more. And I mean, is there something to it in the way the human brain also does things? Like, people talk about procrastination, like, well, all of a sudden you have fewer hours and you are creating so much more. In some sense, we are budget forcing our brains as well. I don't know if you feel like there's any...
Maybe not, because like I think most of the value in shrinking time comes from focus. right? Like if I have 2 days to prepare my talk, I'm more likely to hit a bump and then go check Twitter, uh, and like I don't know, go play with my daughter. Whereas if I have 2 hours, then I'm gonna be like block out everything. I'm just gonna do this. Uh, so yeah, I think that analogy may or may not apply, but there is something to be said about like saying that I don't have time to go deep into rabbit holes. Let's find the solution that I can find without going into rabbit holes, and sometimes that ends up being better strategy.
Yeah, yeah. What else, Alex? Anything else about the paper? I have some sort of more pointed questions and some notes that I've taken as well.
I think the
And,
paper open. Oh, sorry.
no, I was just saying we're kind of running on time, but I
Oh,
did
yeah.
want to cover one topic before we conclude, which is more pragmatic aspect of it. Like, let's say I'm a startup with, I don't know, 15 people, and I'm considering these things. So I have two questions. One is, what are the steps and what are the cost of me making a small bet here that's meaningful? Okay. Like you mentioned 17,000. Where does that number come from? Like how much compute cost, how much engineer cost should I allocate to be able to try something meaningful? And B, what should I expect from that experiment? So I didn't mean to disrupt the thing, but I wanted to allocate time for this so that before we wrap up, we talk
No,
about
it's
this.
fair. Yeah, it's fair.
Yeah, I think that's a very good question. Yeah. So what we see is with a few thousand worked out examples, you can endow reasoning into agents and LLMs. The compute is not much. The compute seems to be with a single GPU or with a single machine and something like 10 to 100 hours. You can fine tune a Quen or a Llama model. The expensive and the difficult and the tricky thing is the data curation. How do you create those 1,000 questions and answers in your domain? So the tooling there is developing right now. You can use Curator. Bespoke Labs Curator is a tool that allows data scientists to see a current question and answer data set, visualize it, ask questions about it, visualize its diversity, visualize its like how much it overlaps with the test data set and so on. But all the action is how do you create the right questions and how do you get the answers in the right format?
So I'll make this more concrete because I've been thinking about this. So let's say that I have a knowledge search, like things that we've been solving with standard RAG. And my thinking is that instead of retrieval process being fixed, if you make it agentic, where you reason about this is the problem, this is what it is, and you have, let's say, an index of the information, then you could work out a much better plan of retrieving the right set of information and then working out the answer. Right?
Yeah.
If you want to do that kind of experiment, could you help me? Yeah.
Yeah, and by the way, we have struggled on this. How do you get the model to invoke RAG? And especially when it's reasoning. So maybe throw some light on, do you just do this with SFT or do you ever have to use RAG for anything? What's the role of RAG at this point?
Yeah, I think everybody's trying to understand this right now. RAG is very good when you're asking questions on a very large corpus of documents and it cannot fit into the context. Now, one way you could do this is just replace your existing LLM in your RAG pipeline with a DeepSeek R1 distilled model and see how well that works for you. That is going to be quite verbose, so it's going to be slower, first of all, because it's going to do all this thinking. But for some types of questions, it may perform better. That's a 0th order step, right? So just replace the RAG LLM. A much better idea is what you were both pointing to is the LLM should decide what queries to call to the vector database. And that takes us to an agentic workflow where the LLM is not just producing text, but rather it's actually doing calls, function calling it's called. So in function calling, the LLM has to learn, again, a vocabulary. It's like you tell me, Alex, to call the vector database, you say /vector database keyword, right? Now, in order for me to do this, you have to show it to me, right? You have to teach me that this exists as a function. And in the same way, you have to show it to the LLM. The simplest way to show it to the LLM is to describe it in the context. You can say to the LLM, hey, LLM, you have this question to answer. To answer this question, you have to go and search in these documents. And here is how you search the document. So you can describe it in, here's the JSON line you write. And that would be like a zero-shot type of way of testing, taking a reasoning LLM and endowing it with a RAG capability. People are testing this. There's a benchmark called BFCL, Berkeley Function Calling, that I think is one of the most popular function calling benchmarks. And we all believe that function calling with reasoning agents will be transformed. And we're working very actively on this. Right now, as far as I know, nobody has tested this in any published paper, but I think we will be seeing a lot of that. The simplest suggestion for engineers is try to use DeepSeek R1 as the answering LLM. That's a zeroth order thing. And then try to describe the tool in the context and see, and then allow of course, there's also another thing you have to do. It's called scaffolding. When the LLM produces tokens, there must be some code that looks at the tokens. And when the LLM says, I want to call the vector database, code has to actually, execute that and put it back, right? So the data scientist must have a scaffolding for the agent, and then hope at a zeroth order step that DeepSeek R1 with the right context learns how to use the tool. The next step is to teach it how to use the tool, of course, and that would require a data set of using the tool.
So maybe just to say this one more time, like when does reasoning intersect with like a fact lookup from a vector database? Like how would the two interview? And I don't even know how my memory works. Like when do I go back to my memory and use that for reasoning?
Yeah, there's two ways, the hard-coded way and the agentic way. The hard-coded way is the RAG. The RAG says, here's a question, you run the vector query, and then you retrieve a bunch of paragraphs, chunks, and you put them in the context. And you can only do this once, and now the LLM has to answer the question. But a much more flexible way is the LLM decides to run a query itself. That is tool use, where the retrieval is a tool that the LLM can use itself. And then it can be adaptive. It can do one query, then realize, oh, I need to search this other thing, do this other query, and so on. This has not been benchmarked as far as I know, and it's a super interesting research direction. How well do reasoning LLMs allow you to reflect and backtrack and self-validate? So if your problems in your previous pipeline was problems where it was lacking such reflection, backtracking, and self-validation, then we hope that it will fix that.
So then is it safe to say that one of the reasoning keywords will be, hey, stop, go do a lookup? Like, could we do that?
Yeah, exactly. So the model will say, okay, to answer like what is Dheeraj's phone number, I have to talk to the phone number database. Okay, I do this by doing this query. Here's the query. And then it will produce a token, and then the scaffolding has to actually execute it, right? So that also is needed.
Yeah.
One of the things that Amit, you were talking about was domains. Like, it's easy to do this with benchmarks, like, the paper, S1 paper, and even the SkyT1 paper talk about these hard problems that they were solving for. And then, of course, there's the generalized tasks. I have another question on that too. But how do you cold start this tracing thing? Because, let's say we have a new domain and the LLMs have never seen any benchmarks, any answers and things like that. So how do you go about doing this in a new domain?
The simplest is manually have 10 questions and answers, like write the golden answer. And the golden answer will be multi-turn. So this is a multi-turn problem because the LLM has to realize it has to do this call. and then it has to use the output of this to produce the answer. So the ideal situation would be to create a small data set, very, very small, of 20 examples, of fully worked out examples. And the other approach is what's called environments. Now, an environment is a way where the LLM can simulate calls and get rewarded when it does something correct. So you would think that you have a playground where somebody asks the LLM a question, the LLM makes a RAG call, it gets rewarded if it's the right call, and then when it produces the answer, it gets rewarded again. So you have to construct this environment, and then if you have such an environment, you start with your untrained reasoning agent that doesn't know how to use your tools, and you run a reinforcement learning technique that looks at those rewards and trains the agent. So these are the two techniques: curate data sets for SFT, or a reinforcement learning environment. These are definitely going to be happening soon.
So when should one use RL versus when should one use SFT? Maybe that's something that I also want clarity in my own head.
If the techniques that the way of solving the problem can be described by examples, or you have a good way of creating examples, you don't need RL. RL is a way where the model will invent ways to solve the problem itself by trial and error. So for example, in chess, we have a lot of grandmasters playing chess. So we can just take the moves they made and just do SFT. And people did this, right? So you can do SFT on grandmasters playing chess, and that alone is a very, very, very strong thing. And then there was this idea of zero. When you hear alpha zero, that means that you didn't use any imitation. It's called imitation learning. Imitation learning is SFT basically, or you see demonstrations. So if you think the range of your problem is pretty narrow, and you can just have two engineers demonstrate the 5 use cases, create a small data set, and then maybe augment it synthetically to make variations just by prompting an LLM, that's a cheap thing to do. And that it would take, you can create a few thousand demonstrations and then run SFT. Now, if you think that truly there is depth to the problem, there is all kinds of tech strategies that the model has to invent, then you have to make an environment.
Yeah. And Amit, go ahead. You had some questions about active learning. I'd love to actually learn more about that too.
Yeah, so this comes from my experience of building ThoughtSpot. Right? So one of the things that we realized was that, as far as any knowledge in public domain is concerned, LLMs are pretty good at it. Reasoning, they're getting really good at it. So why are agents not able to solve some of the automation problems that we try to solve it with? And my hypothesis is that it's all because there's knowledge locked in people's head that is not documented anywhere. And unless you acquire that, it's very hard for agents to do what they need to do. And the thing with knowledge locked in people's head is that it's very hard to unlock it unless you have the right incentives in place and the right structure in place. So that right structure has to be that, like, you taking the least amount of time and giving them the most amount of value that's immediate, right? And so what we did at ThoughtSpot was essentially, if you ask me, hey, how many deals did I add this quarter? Or how many deals did I close this quarter? In the two worlds, the definition of this quarter changes. In one case, it's the creation date. In the other case, it's close date. LLM is not going to know that, but the analyst on the other end is going to know that. When they ask that question, you echo them back and saying, in this question, I interpreted this quarter to be close date. And they might say, no, this should have been creation date, or this should have been like maturity date or whatever, right? And then you ask them why, and they say, oh, winning a deal is same as closing the deal. So when you ask how many deals did we win, it goes to close date. Now, this piece of knowledge is super critical for solving all kinds of queries when you have to make this kind of disambiguation. I'm trying to build a system that generalizes this idea to arbitrary agents, right? So active learning becomes very, very important, where the user asks a question, you try to solve it in the best way that you can, and then have a compact way of echoing it back to the user. and then the user responds to it saying, I like these decisions, I don't like these decisions, and then we incorporate that into
So
the model.
why is that not RL?
So RL, so the difference between RL and active learning is RL is you kind of have a fixed hard-coded reward function, or like whatever way you have mechanical reward function. Whereas in active learning, there is a cost associated with answering a question. In RL, you don't consider running the reward function as a cost. You can run the reward function as many times as you want. In active learning, you're disrupting a human and taking their time and energy. So you have to be really economical about what do you ask and what do you get evaluated. And so, like, how do you be very economical about the questions you ask and get the maximum value out of that?
So how do you
So
get there?
yeah,
Is it from imitation or how?
so if I may draw an analogy here, if I want to, let's say I want to solve a problem as Amit was saying very interestingly, I could passively create 100 use cases, 100 examples, and have experts solve them and create a data set. And that's an SFT data set. In active learning, I would be deciding each example on the fly, so to speak. So I would be not just somebody gave me a data set once, but I can decide what to ask from the experts, and I could decide what to ask on the experts in an adaptive way, even, which is like online is the terminology. But this is still always creating questions and answers. So I'm always doing SFT, but the data set where I'm doing SFT is created in an active way, as opposed to somebody gave. If you just take, MMLU, or you take Amy is a data set of math questions. That's a passive data set. Like if you have a math solver that can answer new questions, that's active learning. Now you have the problem of deciding what questions to ask. And then if you also want to make it adaptive, which I think is related to what Amit is saying, then you have an online component. I think it's a super interesting idea. And I think it's much more data efficient, because one thing is you ask people to solve 100,000 problems, but it's a very different thing that the model can ask back questions. It's like, is that the same as this? Because then you may be able to learn the same thing without 100,000 questions. But as you say, you need experts, and you need experts in the loop.
Yeah.
Yeah.
And in the old world, active learning used to be basically find the examples where you have the most uncertainty and ask the question from there.
Exactly.
You could perhaps do something like that today also, based on like the probabilities of the tokens being generated for the answers, or maybe just ask the LLM that how certain you are. But
Is there any analogy, any sort of patterns from the pre-training days when we use humans for doing some sort of labeling or classification versus what we're talking about here? And how do we map it to the new things we're learning about imitation learning? Like, how would I actually ask it to even ask a question? Is that itself like part of reasoning? Like, where did this intersect with SFT, for example?
Yeah, so I guess the human way of thinking about it, like we've got hour and a half from Alex, and we prepare a little bit and say, like, what are the questions we want to ask Alex so that we create the maximum amount of learning? And there's some reasoning involved in doing that preparation. So how do you get models to do that kind of preparation? That like every user, I can only ask them maybe 10 questions a month. What are the questions do I ask them?
And when do you ask them? Like, if in your reasoning, because let's say we're still talking about the phase of thinking and there's a phase of solution or solving.
Yeah.
Are you talking about the phase of thinking where it'll actually produce tokens to ask questions off of a human?
So my experience, again, building ThoughtSpot has been that like it's very hard to sit users down and ask them questions, right? But if they're in their work stream trying to get something done and you ask relevant questions, then they tend to answer. But you can't bombard them with questions that like every time they come in, before you answer their question, you ask them 3 questions. They're like, what is this thing?
We'll be Clippy. You have invented Clippy. Yeah, yeah,
But
yeah,
but
yeah.
but if you're selective about it, like maybe once in 10 times they come, you ask them a question, then and you produce value based on that question, then they are very happy with it. Kind
But
of
how does
similar
it
to like,
intersect with the physics of next tokens and all this SFT stuff? I'm trying to figure out the how of it. Like, how would we do this?
hmm,
In everything we talked about for the last 80 minutes and the last 10 minutes, like, what's the
yeah.
real connective tissue?
So I think once you get the data from the human, it's the same set of techniques, right? Like now you know this is the correct answer. You can maybe RL your way into thinking tokens that produces that answer, or maybe you just use it directly in SFT. How do you come up with the right question and the right time to ask the question is yet another reasoning problem, and we could try to solve it using the same set
Maybe
of
we should get
techniques.
to it at some point. I know we are 90 minutes, but there's something about you know, prompts versus RAG versus SFT. And I know that, Amit, you made some point about companies who are still doing a lot of prompts with large foundation models, and then this idea of SFT on the other extreme and RAG in the middle. Maybe we need to invoke some response from Alex as well here, and where you are in that overall journey.
Yeah.
I think that nobody has managed to do what you're saying. I think that doing reasoning with RAG as tool use is super interesting, and learning from humans in the loop with active learning is even more, unexplored and very interesting. I think we should, think of a concrete domain and think
Mm.
of how to, and the domain matters tremendously. Okay, if the domain is solving math, you don't need to ask a mathematician what it turns out, as we just learned, to solve math Olympiad problems, you don't need to have a human in the loop. The only thing you need is fully solve problems with correct solutions. That's what we learned.
Mm.
Now we needed a few thousand solve problems with correct solutions. So that was the answer we learned. Now in coding, there is benchmarks like SweBench and Live Code Bench that are driving progress. I think the best way to do the science of this is create a benchmark or an environment, and then, if you want to do it in the open source, you release it in the open source. Otherwise, you have to do it inside your company. But the measuring performance is, I think, the way to go. You say,
Mhm.
here is what we're trying to do. Here's how we're going to measure it. Here's 100 questions, 100 tasks, and here is how we measure if they were done correctly. And from that, you can build. But the number one starting point is understanding your problem by measuring performance. And then I think there's going to be a lot of fascinating research that will be unlocked in the next 6 months to a year. But still, right now, we don't have any answers. The reasoning agents came out, 3 weeks ago. Reasoning became public 3 weeks ago. And S1 and the papers we studied are, 1 or 2 weeks old. So this is a very rapidly deploying landscape. But I would start with measuring progress.
Yeah.
But maybe just this thing about, will prompts be enough for most things versus when will it start to basically break down?
Don't get me
Anybody
started.
who, well, let's at least have people a little bit of a fork in the road. When do they know, you know what, I need to learn SFT?
Yeah. Sorry, again, just to say this point, I have seen so many people that thought that they could solve every problem by just prompting and sequences of prompts, and they call them multi-agent systems. But of course, it's just prompts to GPT, and then other prompts and other prompts and other prompts. And this reminded me of exactly expert systems in the AI of the 80s. That people were just trying to solve problems by if basically glorified, duct tape. I really think that this is not going to. This is not
You know that
working.
Amit is in that school of thought, and he has a PhD from UT Austin on AI. So you're not talking about expert systems right now,
Yeah, in a narrow domain, maybe. Yeah, in a narrow domain,
Mm.
maybe. But I think people learned that these systems were not flexible.
Yeah, Amit, anything on that? Because we have also found our struggles with prompts only, but what are you seeing out
So
there?
there was a very interesting talk by somebody from OpenAI that I liked, where he was saying was that, in the limit, learning and searching is the only two tools you need, like sort of training training based on an objective function and searching through the space is the only thing you need. But it requires a certain amount of compute and certain amount of data to be available for it to work. And at every point in time, there's been a certain window of problems that you can solve with these. And then you could extend that window by using our heads and coming up with a structure, which is what like expert systems are, like a system of prompts or whatever it is. And for that point in time, that is the right solution for that problem. And as the window moves and you get more powerful training systems and searching systems, you kind of destroy the expert system of that era. But then you can extend the systems built purely from search and learning to solve a little bit harder problems. And there's always going to be an envelope around it.
All right. I know we have gone through at least 97 minutes of this. So hopefully our, people who are listening to this are committed folks. But there's a lot to talk about here. I know we are leaving people in the middle of this very controversial topic of where do prompts end and where does SFT begin. There's also an episode to be had where we go all the way from SFT to using SFT for deploying SFT models with agents and things like that. So we can do that within the two teams. There's a lot of unanswered questions in my head about just things relating to RAG and prompts and SFT alone. I think these two papers have been amazing for me. I can tell you that. I'm a whole lot more, 10x more educated than I was before these two papers. I look forward to doing one more of these in the coming weeks. Thank you.
It's been an absolute pleasure and learned so much. Thank you.
Thank you. That was a really great discussion as always, guys.